water isn't always at the bottom. Water tries to find its level, but it doesn't do it instantly. Otherwise, you couldn't have a cliff with a waterfall, right? It would just teleport straight down there. So what you'll have in real life on flat Earth, the water might actually be coming down the mountains, and some of it is going to be cycled up here in evaporation and clouds and rain. So not all the water on flat Earth is going to be down here. Can you even see that? Did I just draw that way? You can't even see that. I almost drew that right where you couldn't see that. Oh well, you can see it well enough. My picture of a waterfall isn't very thrilling. Here, I'll replay it for you so you can see. Okay, there is the waterfall. The Earth, of course, isn't completely flat, because if it was, there wouldn't be any hills now, would there? There wouldn't be any hills, there wouldn't be mountains, there wouldn't be any valleys, and it's not just a sheet of glass. That means that some of the water in the cycle of water finding its own level is not at its own level because it's moving around. It gets up and it comes down, and some of it soaks into the ground. It takes a while to come out as springs and streams and things. So what we have on our flat Earth is very similar to a lot. Because there's hills and valleys, some places, I'll draw an ice wall there, some places will be low around the edge, and some places around the edge might be high. So this edge is actually lower than this spot on this edge will actually be lower than this spot on this edge. All right, that's okay. This will fill up with water, but not completely full because we've got water in that cycle, remember? So what has happened with our planet is this. You have a mountain and you have a valley. Now, these sides here aren't exactly straight on mountains or valleys. They're actually kind of like this and like this. You know? So they're not perfect angles like I oops, didn't say fuck, did I? Like I drew there. They're not perfect angles. So what you have with a mountain is you got its point up at the top. And if you take a plumb bob right there, you can draw an imaginary line through the mountain. Right? Okay. Now you'll have a valley next to it. Of course, it won't look like that at all. It'll look like this. But if you were to take the bottom point here and line up a plumb bob with it, you could draw a line through that. And what you'll find is that these two lines aren't quite exactly parallel. Now, the reason that they aren't parallel, the law of large numbers says that if you were to take all the ups of the mountains and all the downs of the valleys, the sum of those things, the sum of all the heights, wouldn't be equal to the sum of all the depths, how deep it is. What's the chances it's going to work out that way? What's the chances that they'd be exactly the same? Well, almost none. And that's the case in our Earth here. So what happens is, because these sides are slightly angled, the apex through the center of these are slightly off center. Now, if the sum of all the depths is greater than the sum of all the mountain peaks, all the heights, then that means that these would be spread apart. So these two angles will actually be slightly V-shaped. Very, 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 very slightly. This will be a tiny bit further. What happens at the next mountain is the same thing, except it's even further off from the original. you keep adding mountains, and mountains, of course, aren't. You look from the top down on a mountain. Let's say this is the crest of a mountain. Mountains aren't necessarily in a straight line, and sometimes a crest of a mountain, like here, is actually lower than this bit here. So, coming towards us, it's lower still. So your mountain and valleys go up and down in all directions. You'll have a peak at some point, and then it'll go down. You'll have a bottom valley at some point, and it'll go up. So all the directions. What we have then is eventually, when you have enough peaks and valleys, and the depth is greater than the height, eventually the differences in angle between here and here will add up to be 360 degrees. And I'm writing 360 degrees down because when you write something down, it proves it's right. So eventually these will all be 360 degrees. So what that means is that the very last valley right here, the furthest one away from where we started over here, is going to be arced, and it's going to be lower by 360 degrees, which means it'll actually be right there. This will go all the way around, it'll be right there. And it'll do that both directions. So what we have is mountains, greater depth valley, mountain, greater depth valley, mountain, greater depth valley, mountain, greater depth valley, mountain, blah, 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 until it has gone all the way around. And one edge, this edge of the flat circle, is well, this edge is much, much higher than this edge because this is a valley. And so it's gone all the way around. So what we end up with is, of course, that's not to scale. To scale, it would just look like this. All little valleys and mountains add up. And that's not an oblate spheroid. And quite frankly, neither is Earth. Earth is not an oblate spheroid. The difference between one direction and another, even hypothetically, is so minute that it falls well under, what is that? Is that a sphere or an oblate spheroid? Is it a pear? No, it's not a pear. It's not an oblate spheroid. It's too damn close to being a sphere, and you're just being pedantic if you want to call it an oblate spheroid. Regardless, what happens on Earth, with our flat Earth, is it becomes three-dimensional. So we have a flat Earth that has the navigational properties of a sphere. But it's not a sphere, clearly. It's not a sphere. Clearly it's flat. Everybody knows that. You look around and see it's flat. You can look at the ocean and see it's flat. Even though, oceans have waves too, but that doesn't count. Because just like the ground having waves, it doesn't count. Unless you take into account the difference in height and the difference in depth. The difference in height and depth between the two on our planet, and this is demonstrable. You can go and make these measurements yourself. You can see that on our flat planet, the total sum of all the depths is greater than the sum of all the heights. And that puts us into a sphere in both directions, all directions. This is north, all directions. Until they come back in, and it's just... So we have a flat Earth, and all the navigation that we do on it. This is the reason why Flerfers have such difficulty with navigation, is because they don't realize that the contours. When you measure distance, if you just measure across the ground, this distance of a mountain going up and over is much further than just this. And they have to take into account, when you're going places, this additional distance. Okay? I mean, even bees do that. They don't account for the distance over the top, they account for the distance around the side. But even bees, and they've got what, 100,000 neurons, they're really dumb, but they can dance pretty good, and they can communicate. So even bees have to tell you that you have to take the distance that you have to go around things. So when you account for all the ups and downs, the navigational properties of our flat planet is the same as a sphere. QED. We live on a flat planet. And you can prove it with your own demonstrations. If you go and measure all the valleys and all the peaks and their axes, their apex axes, you will discover that they're just slightly like this. Now, I way overemphasize that because otherwise, I mean, how would you know? I don't have a piece of paper the size of the planet. Duh. Well, not this planet. There might be other planets, but if they were the size of this piece of paper, they probably wouldn't have cleared their orbital path, and therefore it wouldn't be called a planet, like poor Pluto, which should be a planet anyway. But regardless, that's what's happening on our... Now, other flat Earths, the peaks may actually be greater than the valleys. And what that would do is make it like this, and we'd be living on the inside of a wheel-shaped thing. And we're obviously not living on the inside of a wheel-shaped thing. We can see that. We can see that there's no wheel going over top of us. So therefore we're not shaped like this. And the two sides, the two edges of the flat Earth have to be, what's the chances that they're going to all be exactly the same level? None. They have to be a different level. So eventually that level, there. And that's why you globetards and your navigational airplanes and things like that can fly on the flat Earth and not get thrown off, because this flat Earth that we're on has the navigational properties of a sphere. And you can prove that with measurements, and that's been proven over and over and over. Now, you might ask why people don't fall off down here. Well, that's because our flat Earth has a center of gravity that pulls down all along the ways. Otherwise, when you're at the edge, you'd be standing crooked because gravity would be pulling you crooked. But there isn't really gravity. It's magnetics. It's gravitomagnetic power, and that pulls straight down. But because our flat Earth has curved like this, one side so much lower that it's come back to the rest, that every time it pulls straight down, it's changed a little bit. And that means that the water just goes around and around in circles. And in fact, that's what we find when you look at the path of water in the oceans. I'm gonna draw an ocean. I don't know. You know, they have a path of water moving through the ocean that goes like this, and they have little fires on it, and they show you that it's moving. And that's because it's always going downhill. See, if this is sideways, if this is north, and this is not really south, but we call it south because it's not north, and because the flat Earth has curved all the way around. So this is why the water doesn't fly off of the flat Earth, even though it's navigated like a sphere, because it's continuously going in a stream, and it makes these kind of wiggles in the same way that a river has meanders. A river won't go more than 10 times its own width before it has a meander. Rivers meander. I mean, they meander all over the place, and that's exactly what it does out in the ocean. It's meandering all over the place. Part of what keeps this moving is the fact that the moon has a whole bunch of magnetogravitational force, and the moon keeps moving. So the moon keeps changing where the high spot is, so to speak. But here's a high spot, and water will run away from it. And then as the moon goes to a different place, over here, the high spot will be over here, and then the water will run away from that. But the moon keeps going around and around the sphere, and that keeps pulling the high spot of the water. So the water keeps traveling as if it's on a treadmill, literally on a treadmill. Now, a bunch of this water, in its process, gets evaporated up into clouds. And these clouds then are also being pulled around. And eventually these clouds will get somewhere else and they'll drop the water back at the beginning again before the water has gotten to the end. That's why the edge of flat Earth never fills up with water. Otherwise, if the edge of the flat Earth filled up with water, all the rest of the Earth would have to be completely bone dry. And it's obviously not. It's raining right now where I'm at, so it's obviously not. And water takes time to go through its path to get to a level. This accounts for exactly why and what we observe on our flat Earth. And if you want to fly from one place to another, you can just fly around the pole. See? QED. We live on a flat Earth with the navigational properties of a sphere, which also affects the weather. And this is the reason why there's such a difficulty in demonstrating why a flat Earth is flat. I don't know how to end this, so bleh. Okay, in this addendum, I'm going to explain who the most powerful Sith Lord of all times ever was. And I'm going to give you a demonstration of how we know this. And it's going to surprise you. It's far more powerful than Plagueis and Sidious and Dooku and whoever that general with the robot arms was. Their names don't even matter in comparison to the very most powerful ever Sith Lord. And that Sith Lord was one who actually did completely defeat death. Has never died, not even yet. And that person is Mary Poppins. Now, the reason we know that is because there's a little bit of her song, her favorite song, goes a little bit like this. Boom, boom, ba-doom, boom. A spoonful of sugar helps the medicine go down. A spoonful of sugar helps the medicine go down. A spoonful of sugar helps the medicine go down. The medicine go down, going down, going down. Spoonful of sugar helps the medicine go down. Medicine go down, boom. You see, the Darth Vader Imperial March theme is a copy of her spoonful of sugar helps medicine go down song. Um, she's clearly able to force jump, and she's able to do so quite gently. She everybody thinks she has an umbrella, but that really is simply just a lightsaber that has extra options attached to it. So the next time you see Darth Vader walk in someplace and you hear the theme song, just remember that Mary Poppins was a lot tougher than him, and he was so impressed with her that he used her music. Spoonful of sugar, some medicine, go down.